Good afternoon. Welcome to Krishna's class. We look at the orthonormal sets and how it enables us to identify the vector that lies closest to a given vector in a subspace. Okay, so this is an advantage that you have in a Hilbert space because you can talk about what are called orthonormal sets. Now we shall begin with an example. The example is something that is very familiar to you. I mean, I'll take two examples. One from the in R3, our famous our most favored example. Take. We look at the following examples. We take R3. R3 with the usual inner product. We designate it by so okay. The usual inner product. It is if x1, x2, x3, y1, y2, y3 are the two vectors, x and y respectively, then it is the dot product of x with y that we take as the inner product. This is the usual inner. So x now let's just take an orthonormal set. We will consider E1, E2, E3 form an orthonormal set in so this forms an orthonormal set in R. So what you have is this, that EI, EJ and E1, E2, E3 is the usual this is what you have, and this is actually EI dot EJ. That is this. So the vectors are, you recall, EI, E1 equal to 1, 0, 0, E2 equal to 0, 1, 0, E3 equal to 0, 0, 1, and then you have this property that EI, EJ, the inner product is nothing but the dot product of EI with EJ is equal to delta ij, that is it's equal to 1 when I equal to j and equal to 0 when I is different from j. This is what we have. Okay. Now let us take a fascinating situation. Consider the xy that is in north. Then you see that this is spanned by that is every vector in the xy plane is a linear combination of E1 and E2. Okay, that's what we mean by the span by E1. That takes care of all vectors in the xy plane xy space. Now what you have? You have in x is essentially equal to this is true for every x belonging to. So this I can rewrite as x equal to x1 e1 plus x2 e2 now e1 x1 x2 x3 are the coordinates with respect to the ordered basis E3. Now this is very easy to calculate. You take, so x1 is equal to E3. Now this is very easy to calculate. This is just taking the dot product. So this is how you have x1, x2, x3, and then these are called, so we will give a very sophisticated name for this for some other reason. That is, these numbers are called the Fourier coefficients of x. Now take x y defined by or I'll put this way, u defined by x1 e1 plus x2 e2. I drop that. Okay. So this belongs to what you call xy. That is R2. Right? Let V be defined as some y1 e1 plus y2 e2 xy plane. Now you see that u is the orthogonal projection of x onto So I mean, okay. So this is x1, this is e1, x1, x2, x3 are points on this. So this is the orthogonal projection of x to the this is the orthogonal projection of x to, so this is the one, this is u. Okay. Now what you can immediately see, it's not difficult to see at all. Okay. See that the distance from what is that you can see immediately is that the x minus u square is certainly less than or equal to norm of x minus v. So v is some vector. So what you have is, this is norm of x minus v, this height. Okay. Sorry, x minus u, and this height is what you call, or yeah, this distance is what you call. So this is and you have this inequality. What does it say? It says that if you take any vector in the subspace spanned by E1 and E2, then the distance of x to that vector is greater than or equal to, that is, I am talking about greater than or equal to the distance of x to u. What is u? U is created out of the Fourier coefficients or using the Fourier coefficients of x. Okay, that is a speciality. Whereas this is not, this is an arbitrary vector that is picked up in R2. Okay, so this is one of the results that you can immediately prove, and it's not difficult to see at all, because you see that after all you can use orthogonality. So you have a what you call right angle triangle, and this is the length of this particular vector, that is length of x minus v is square is equal to length of x minus u square plus length of u minus v square. That is the what you call the Pythagoras theorem, and then it is immediately clear. Okay, so we will take a more sophisticated example. So this is very simple one that you have where you have a feeling, and in fact I can just make this a bit more visible by choosing B somewhere here. Now what I do is I choose this V as something like this. This is V, and then x minus V. The length of x minus V is the straight line that is joining x with V. This is the length of that, and the square of that distance. So you get a sort of right angle triangle here, and then it is obvious that norm of x minus u, that means the square of this height plus the square of this distance, will give you the square of x norm of the square of the length of x minus v square. So that is simply Pythagoras theorem. Okay, so let us now go to a more sophisticated example. I'll take the example 2, which is from the Fourier series, a more sophisticated version of what we have done in R3 now. Okay. Now we consider take the second example. Second example is in the L2 space. So consider L2 minus pi to pi. Okay. So this consists of all complex valued functions defined on the interval minus pi to pi it forms a linear space, and with the inner product the where f and g are such that you can show that L2 minus pi defined as the set of all f such that Now this is a Hilbert space. Now one can show that the collection one by root 2 pi e to the power I n t form an orthonormal sequence on so this is the orthogonality property combined that with normalization, you get this result. Okay, that's quite easy to check, and this is a very classical result. Okay. Yeah. Now let us rework this result. What does it say? See, I'll come to the interpretation of this later, but before that, let me complete the notations. Okay, so this is an example. Now, we'll take the more generous case. You can take this as an example for that. So let an orthonormal sequence on AB. What does this mean? It means delta L. This is the property that you have. So you are taking all L2 functions on the interval AB, all complex valued L2 functions the interval AB. So that means we consider L2 this is again a Hilbert space. So L2 is a Hilbert space. Okay. Now we take up a partial collection. Okay, we can do the following. F belongs to L2 AB. We can compute complex numbers Cn defined by and these Cn's are called the Fourier coefficients of now this is of course from the classical work of Fourier trying to expand an arbitrary function in terms of a sequence of rather nice functions. Okay, now you can see that these are all nice functions. So e to the power int is a very nice function. It's smooth, it is differentiable, and it is C infinity function, and so on. So all sorts of nice properties are there where an f may not have this. And what you have is this. See, fx can be approximated. I mean, this is. See, there are two things. One, the given f, and then there is a infinite series that comes from here. This is called 1 to infinity Cn by okay. We do not write equal to here, we just put it this way. Okay. So this is coming out of this. One of the questions is when they are equal, in what sense they are equal, and so on. Okay. So this is in L2 AB. This is of course belonging to span of this collection phi n. For the closure of this. Okay. Or I will write here each belongs to the span of phi. Okay. Why I am taking very specific care? When I talk about the span of phi n, I mean only finite sums are taken into account. So this is something that you have, and this of course this infinite sum is in some sense the limit of a sequence of finite partial sums that you can construct using phi n. Now you see that each partial sum, finite partial sum that you can take out from this is very smooth function. It's a smooth class of functions, whereas your f need not be that. Okay. So, in what sense these are equal? This is one of the basic questions that you encounter in the study of Fourier series. In fact, the mathematics came. See, in the Fourier series was introduced in the context of say heat studies on heat and rather heat equation, and then all sorts of very intricate questions came up, because it was formally, one would have loved to write fx equal to sigma n equal to 1 to infinity cn phi n. Is it possible? Now these kind of deeper questions came into picture. Now let us come to the theme of what we are trying to work. We have already seen it in R3. We'll look at this in L2. Now you take S n defined as sigma m equal to 1 to n Cm well defined. Say it's a finite sum that you are talking about, so there is no complication at all. Well defined. So Sn is a partial sum of the so-called Fourier series that you have. In fact, Snx is a vector which is a linear combination of phi m constructed with the Fourier coefficients. So these are the numbers that we take are the Fourier coefficients. Okay, so that's the important part of it. Now you take another Tnx. Now this belongs to span of so you are taking n vectors phi 1, phi 2, etc. phi n and taking the span of that. So this is an element of the span of this. Now you take Tn to be once again this belongs to span of see the point is this. See, this is Sn is constructed with the Fourier coefficients. Okay, whereas Tn is with any set of scalars that you have or any set of complex numbers. Okay, now what one can prove is this. Then this is what you have. The distance from F to Sun is less than or equal to distance from F to in short, Sn gives you the vector whose distance from F is the smallest from. So Sn is the vector in span of whose distance is the smallest from F. Take the corresponding situation in R3. Okay. That is what this result says. Because this is an arbitrary vector in the span of phi n, whereas this is a specific vector which is constructed using the Fourier coefficients of f. Then the distance from f to Sn is the smallest distance compared with the distance with f to Tn for any Tn in the span of. So this is the theorem. This is one of the results that you have. Therefore, you see that the collection of phi n's, I mean, these computations are very simple once you have the vectors as orthonormal vectors, and the orthonormal vectors enable you to take the to identify the vector that lies closest to a given vector in a subspace. Okay, so this is the advantage that you have. Now let us try to do the formal work. So it is very easy. So we will start with the main theme of the lecture. The Hilbert space or the complex field let an index it alpha designating an arbitrary element. Okay. Now we define what is an orthonormal sequence. Definition. A collection U alpha is the index set. I mean, this index set need not be countable, need not be finite. Okay? Could be even uncountable. So we are taking the general selection. H is said to be orthonormal if inner product of alpha to beta equal to 0, our alpha is not equal to beta, and so here alpha beta belongs to the index set A. This is the orthonormality condition. Remember E1, E2, E3 or the e to the power 1 by root 2 pi e to the power I n t. So that connection. They are all the examples of that. Let x belonging to, now define to alpha. Alpha. Then x hat alpha are called the Fourier coefficients of x relative to the orthonormal set index set. Now what we do is we begin with the assumption. First consider A to be finite, or we shall take where f is finite. Now that's a specific case that we are interested in. Then we have the following. This is exactly what we want to. And that theorem is essentially what we have stated there in the case of Fourier. The classical Fourier series. Okay. Let orthonormal set let f contained in A be a finite now we are not assuming A may be finite, A itself may be infinite, it may be countable, it may be uncountable, all sorts of possibilities are there, so that they are not ruled out. So A may be even uncountable. Okay. So I'll just put it here. It is better to somewhere else. That A, yeah, I think I have said that earlier. A need not be finite. A can be countable or uncountable. So just keep it. Let defined as alpha belongs to F. So that means you have a finite set of elements U alpha, and you are taking the linear combinations of all those vectors. Then MF is a subspace. Okay. So we make the following statements. Finite dimensional subspace of, in fact, to be precisely, to the number of elements in this is the number of elements, or this is the cardinality of, that's what it, because you see that all these U alpha which belong to alpha belonging to F, because they are orthonormal, they form a linearly independent set, and those linearly independent sets span MF. Therefore, you have the dimension as the number of elements in. Okay, then we have the following. First statement is that complex valued function that is phi is defined from A to C. That means associate with alpha a complex number. Each alpha you associate a complex number to phi. So we take phi in a particular way. Take phi identically equal to 0 on A slash. The complement of F in A, we take phi identically equal to 0, by which you mean that phi alpha equal to 0 for every alpha belonging to that is, when it is not in F, we will have it necessarily equal to 0. So there exists a vector y belonging to F defined by how is this y defined? Y is defined as a linear combination of U alpha for alpha belonging to F, but the coefficients are picked up as the if you are talking about a vector, the Fourier coefficient of y equal to sigma alpha belonging to F y alpha U alpha, where y alpha equal to or rather y hat alpha is equal to or I would say okay. then y hat alpha, phi alpha, where y hat alpha is the Fourier coefficients of one. So with phi, you construct a function y, and then you have y hat alpha, that is the Fourier coefficient of y is equal to phi alpha. So that is one of the results. This is true for every alpha belonging to A, in fact, because it is going to be 0. Okay. Also, so this is the first part of the theorem. The second part of the theorem is what we observed in the previous case. If x belonging to H and SF equal to hat alpha u alpha x to alpha then what we have is this norm of S is less than for every S is any vector which is obtained as a linear combination of vectors in the collection U alpha where alpha belongs to F. Okay, that means any linear combination of except for you get equality for S equal to SF when equality holds. So we have a nice inequality also. Nice inequality that I is the so-called Bessel's inequality. we have this is called the Bessel's integral. So let us prove this here. It's quite easy to prove. This is just looking or making some little computations. Part of A. Take y to be equal to the given y. Then we have y hat alpha. This is the Fourier coefficients, and I will put it this way, right order. Inner product of y with alpha, which in turn is equal to phi alpha, using orthonormality. Yes. So that's very easy. You take the dot product of y with u alpha, and then use the fact that u alpha u beta inner product is equal to, the properties of inner product, u alpha u beta equal to 0 whenever alpha is different from beta. Then you end up with u y hat alpha, which is a Fourier coefficient of y, equal to. This is the first part. Further, you take norm of y square, take the inner product of y with y, which inner product of this with now you simply use the properties of the inner product, and that would immediately give you the statement for the or the square of the norm of vector phi in terms of the phi alphas. That is the, this is in a way the restricted Parsifal's quality. That is, when you just consider the subspace MF. Yes. Now let us prove the other part. So we'll so that is which is equal to Q alpha. This is what. Okay. So you see that S hat is equal to using part A. This is immediately. Now you take x minus SF. X minus SF is orthogonal to U alpha for alpha belonging to F. That's very easy to work out. X with U alpha, the inner product of X with U alpha is X hat alpha. The inner product of S with U alpha, this is the Fourier coefficient of SF, which is also equal to X hat alpha. Therefore, this is this with U alpha, the dot product is 0. That's very easy to see. Okay, just because this will become simply X hat is equal to, this is what it is. Okay. Which implies X minus SF is orthogonal to SF minus for every S belonging to L. Why? Because SF minus S is essentially SF okay. Now you can easily see that this is summation over alpha belonging to F, and this is orthogonal to every U alpha for alpha belonging to F. Therefore, that's easy. So what you have is the following. What is that you can infer from this? X minus Sf equal to therefore you have this is equal to 3. This is quite easy to see, okay? Because this involves only alpha belonging to F. This involves only alpha belonging to A slash. Therefore, their inner product is equal to 0. Consequently, this is equal to norm of x minus Sf plus whole square, and these two are mutually orthogonal. Therefore, this is equal to this is what you call the Parseval's equality or orthonormal, or what you call the Pythagoras theorem. For these two vectors, because these two vectors are mutually orthogonal. Therefore, you get this result, which then implies norm of x minus s whole square is greater than or equal to norm of square. Okay, because if you drop this, then this is what you get. Okay, so this could be smaller, and equality holds if and only if s is equal to x. Otherwise, this will become, therefore, in general, you have for any set belonging to MF, you have the following. Is less than, strictly less than minus S. Okay. So in other words, this is what you have. So this is one of the inequalities that you want. Further, suppose you choose S equal to 0, then norm of SF square is less than or equal to norm of square. And this, of course, you can prove like this. So square. This implies x square. That is, this is what we call, this is by choosing S is equal to 0 in this inequality. This is called the Bessel's inequality. So let us now sum up the whole thing. Okay. So let me just sum up the whole thing. What we have. You have, this is H, side versus within the product. Now you have what you call a dual. Okay. Now you take F contained in A and you have MF as defined before, span of so you have MF is a subspace. What does this say? What does this theorem say? Take any x in H. Okay. Then there is a vector, okay, which you call SF. So that this is the distance from X to SF, or what you call the orthogonal projection effect. Okay. This is a vector in SF because it's a linear combination U alpha with the property that this X minus SF is orthogonal to every vector is in MF. So Sx minus SF is orthogonal. This is the first thing that you have. Now the second part says the following. Suppose you take S belonging to MF. Any S belonging to, then the distance from X to S is always greater than the distance from X minus. That means the following. See? And equal or except when equality holds. Or S is a vector, or what you call SF is the vector closest to X among all vectors S belonging to M. This is the sum and substance of it. Therefore, you see that it is very nice or very easy to identify SF. How is SF identified? It is easily identified using what are called the Fourier coefficients of X. Now see that such a vector, that is identified as the following linear combination. What is it? You take the Fourier coefficients of X and alpha belonging to. So this is so there exists a unique vector denoted by Sfx which lies closest to X, and it is given as a linear combination of the orthogonal set of orthonormal set of vectors U alpha. So these orthonormal vectors, so the work is done provided you just compute this X hat. Okay. So now what you do is you try to go back to R3 as well as the Fourier series and then try to find out what exactly. Okay, thank you very much. I stop here.